CS407, Numerical Analysis, Section 10.3, some small simulations. In this section we'll illustrate the idea of simulations through some very small examples. These won't be large-scale simulations, since that's probably beyond the scope of what we're going to be able to do in one day worth of class, but we can certainly do some small simulations. So, in particular, we're going to look at some physical situations in which an element of chance is present, and try to imitate that situation on the computer. We can draw statistical conclusions if we can conduct the experiment numerous times and see what the outcomes are. Example applications of simulation are client-server simulations. Certainly you can use simulations for modeling queues, for modeling traffic through networks, and for games of chance like in artificial intelligence, where you will do rollouts for games such as Baccarat that have an element of chance yet are dictated on strategy. Let's take a look at a simulation involving a loaded die, which is something we might find during a field trip to Las Vegas. So suppose, for example, we want to simulate the throw of a loaded die, and the probabilities of the various outcomes are in the following table. Probability of 1 is 0.2, 2 is 0.14, 3 is 0.22, 4 is 0.16, 5 0.17, and 6 0.11. So, in these simulation problems, we often need to produce random variables with a prescribed distribution. If the random variable x is uniformly distributed in the interval 0, 1, then breaking this into 6 subintervals with links given in the table, we can actually simulate the throw of the loaded die. So, if x falls between 0 and 0.2, we say the die shows a 1. If it falls between 0.2 and 0.34, we say that it shows a 2. I assume that you made your saving throw against math, so let's look at some pseudocode to count the outcomes of 5,000 throws of this die and compute probabilities. So here's the pseudocode for simulating this loaded die. Here the array y is going to contain the original distribution, and we count the number of times that a result falls in each category using the array m. When this experiment is run, 5,000 throws of the die, the authors got a result of 0.2 for rolling a 1, 0.13 for rolling a 2, 0.2252 for rolling a 3, 0.16 for 4, 0.17 for 5, and 0.10 for a 6. And these are pretty reasonable approximations given what we had in the distribution table. Let's take a look at another example that you may remember from CS 141 and 241, and that's the birthday problem. So this is an interesting problem that can actually be solved using simulation. It also has an analytical solution. Suppose that you have a room full of n people. Each of the 365 days of the year is likely to be somebody's birthday, or equally likely to be somebody's birthday. From probability theory, it can be shown that, contrary to intuition, you only need 23 people to be present for the chances to be better than 50-50 that at least 2 of them will have the same birthday. And it's always fun to try this experiment in a large party or in a class to see if it works in practice. Many people are curious about the theoretical reasoning behind the results, so we're going to take a look at that briefly before moving on to the simulation problem. So, theoretically, after someone has asked his or her birthday, the chances the next person asks will not have the same birthday are 364 out of 365. The chances that the third person's birthday will not match those of the first 2 are 363 out of 365. The chances of 2 successive independent events occurring is the product of the probability of the separate events, as you may remember from 141. Sequential nature of the explanation does not imply that the events are dependent here. So, in general, the probability that the nth person asked will have a different birthday from anyone who's already been asked is 365 times 364 times 363 times 365 minus m minus 1, all divided by 365. And so the probability that the nth person asked will provide a match is 1 minus this value. So what we can do is we can make a table of the quantity 1 minus 365 times 364 times 365 minus n minus 1, all raised to the 365th, divided by 365 to the n. Table 10.1 on 500 shows the result with 23 people. The chances are 50.7%. With 55 or more people, chances are 98.6%, are almost theoretically certain at least 2 out of 55 people have the same birthday. So, without using probability theory, we can actually write a routine that uses random number generator to compute the approximate chances for groups of n people. Clearly, all that's needed is to select n random integers from the set between 1 and 365, and examine them in some way to determine whether there's a match. By repeating this experiment a large number of times, we can compute the probability of at least one match in any gathering of n people. One way of writing a routine for simulating the birthday problem is as follows. We use the approach of checking off days on a calendar to find out where there is a match. Of course, there are other ways of approaching this problem. Here we see the function probability that calculates the probability of repeated birthdays. And that's given at the top. The logical function birthday, given at the bottom here, generates n random numbers and compares them. It returns the true value if these numbers contain at least one repetition, and false if all the numbers are different. Here we can see a comparison of the theoretical and the simulated approaches to this problem. And you can see at 23 the theoretical surpasses 50%, as does the simulation, and they're actually fairly close. Now let's take a look at another problem where we can get a simulation solution. This is called Buffon's needle problem. So imagine the needle of unit length is dropped onto a sheet of paper and it's got parallel lines on it 1 inch apart, or 1 unit apart. What is the probability the needle intersects one of the lines? So we can assume the center of the needle lands on between lines at a random point. We assume further that the angular orientation of the needle is also random. And finally, we assume that the random variables are drawn from a uniform distribution like we've been doing so far. So let's take a look at an illustration of this. Now, here you see the distance of the needle from near the two lines is going to be denoted as u, and the angle of the needle from the horizontal is going to be denoted as v. The needle will intersect one of the lines if and only if u is less than or equal to 1/2 sine v. So what we're going to do is we're going to perform this experiment numerous times, and because of symmetry we select u from a uniform random distribution on the interval 0, 1/2 and v from the interval 0 pi over 2. We determine the number times 2u is less than sine v, let w equal 2u, and then test w is less than sine v, where w is a random variable in 0, 1. So here's the pseudocode for Buffon's needle problem. The program follows the technique discussed in the previous slide and prints out the intermediate answer so that their progression can be seen. It also prints out the correct theoretical answer of t is equal to 2 divided by pi, which is approximately 0.63662 for comparison's sake. Next we'll take a look at an example that lends itself to an analytical solution again. Consider tossing 2 dice. For an unloaded die, the numbers 1 through 6 are equally likely to occur. What's the probability of throwing at 12 and 24 throws of the dice? Well, in terms of an analytical solution, there are 36 possible outcomes. Only one is a double 6, so 35 out of 36 are not correct. With 24 throws, we have the 35 out of 36 raised to the 24th as the probability of the wrong outcome. So, the probability of getting the right outcome is 1 minus 35 over 36 raised to the 24. And that's equal to 0.49140. You can recognize this as the Chevalier-de-Méris problem. The probability of getting at least 1 6 in 4 rolls of a 6-sided die is 1 minus 5 6 to the 4th, which is equal to 0.1577, which is slightly higher than getting a double 6 in 24 throws of the dice, as we've discussed here. This problem, why there was a difference between these two games, led Pascal to begin developing the theory of probability. Unfortunately, not all problems of this type get quick analytical solutions. So if we want to simulate this, a single experiment consists of throwing the dice 24 times. We need to repeat the experiment a large number of times, say 1,000. For the outcome of the throw of a single die, we need random integers that are uniformly distributed in the set 0 or 1 through 6, and we can do this by having x as a random variable in 0, 1, and taking 6x plus 1, which will give us a variable in the open interval 1 through 7, which when we drop the decimal part, we get an integer that ranges between 1 through 6. So let's take a look at the code. Here's the pseudocode for doing the 2 dice problem. Here we get a probability of throwing 12 and 24 throws of the dice as 0.487. The author describes it as approximately even money, but it's about the odds you would get at slot machines. It's a little better than roulette, but less so than blackjack. Finally, let's take a look at a physics example. And our physics example is going to be a simple model of neutrons penetrating a lead wall to see if we can build a lead wall that will protect us from radiation. So, it's assumed that each neutron enters the lead wall at a right angle to the wall and travels a unit distance. Then it collides with the lead atom and rebounds in a random direction. Again, it travels a unit distance before colliding with another lead atom. It rebounds in a random direction, and so on and so forth. Assume that after 8 collisions, it spends all of its energy. Assume also that the lead wall is 5 inches thick in the x direction, and for all practical purposes, infinitely thick in the y, so it goes up as high as we need it to go. What percentage of neutrons can be expected to emerge on the other side of the lead wall? Well, here we let x be the distance measured from the initial surface where the neutron enters. Now from trig, we recall that in a right angle triangle with hypotenuse 1, one side is going to be cosine theta. Now cosine theta is less than or equal to 0 when when theta is between pi over 2 and pi. The first collision occurs at point where x equals 1. The second when x is equal to 1 plus cosine theta. The third when x is equal to 1 plus cosine theta 2. Now, if x is greater than or equal to 5, then the neutron got out successfully. If it's less than 5 for all 8 collisions, then the wall has shielded the area from that neutron. We can build the pseudocode for this, and from a Monte Carlo simulation, we can use random angles theta sub I in the interval 0 pi, because of symmetry. After running this, we can say that approximately 1.85% of the neutrons can be expected to emerge from the lead wall. That's it for today. These are some simple simulations, but you can teach entire graduate courses in simulation and modeling of large-scale computing phenomena. So what we can get done in 1 day of word chaining is a little bit less than that. So next time we'll start looking at linear programming problems.